Mount Rainier rises above the surrounding landscape, with an authority that is difficult to ignore, a stratovolcano shaped by cycles of eruption, collapse and glaciation over hundreds of thousands of years. Its slopes, draped in ice and carved by deep valleys, have long concealed a restless interior. Now, a renewed sequence of nearly 100 small earthquakes has drawn attention back to the mountain's internal structure. The return of this earthquake swarm raises a set of precise and grounded questions. What is shifting beneath the volcano's flanks? How do these clustered tremors relate to the architecture of magma storage and hydrothermal circulation? And why does this particular volcano, among many in the Cascade Range, repeatedly produce such swarms without necessarily leading to eruption? The recent activity consists of dozens upon dozens of small magnitude earthquakes, most too weak to be felt by people in nearby communities, yet clearly recorded by sensitive seismic instruments positioned around the volcano. These tremors are concentrated along the upper flanks, occurring at shallow depths measured in a few miles, roughly 3 to 6 miles or about 5 to 10 kilometers beneath the surface. This depth range is significant because it corresponds to the upper portions of the volcanic plumbing system, where fractured rock, heated fluids and residual magma interact in a complex and dynamic environment. Mount Rainier is not a simple cone of solid rock. It is a composite structure built from alternating layers of lava flows, ash deposits, and fragmented volcanic material known as tephra. Over time, these layers have been altered by heat and fluids circulating through the mountain, creating zones of weakened rock. These hydrothermally altered regions are particularly important because they can influence how stress is distributed and released. When pressure changes occur, whether from fluid movement or subtle shifts in the crust, these weakened zones can fracture more easily, producing clusters of small earthquakes rather than a single large event. The Cascade Range itself is the product of tectonic forces operating along the western edge of North America. Offshore, the Juan de Fuca Plate is being forced beneath the North American plate in a process known as subduction. As the oceanic plate descends, it carries water-rich minerals into the mantle. Under increasing temperature and pressure, these minerals release fluids, lowering the melting point of the surrounding rock and generating magma. This magma rises through the crust, feeding a chain of volcanoes that includes Mount Rainier. Rainier's magma system is not continuously erupting, but it remains active. Beneath the volcano, magma does not exist as a single large chamber filled with molten rock. Instead, it is more accurately described as a network of smaller pockets and partially molten zones embedded within solid rock. These zones can expand, contract, and shift over time, influenced by the supply of new magma from deeper levels and the cooling and crystallization processes occurring within them. The earthquake swarm currently being observed is consistent with the behavior of fluids and gases moving through this complex system. As magma cools, it releases gases such as water vapor, carbon dioxide, and sulfur dioxide. These gases can migrate upward, increasing pressure in fractures and pores within the surrounding rock. When the pressure exceeds the strength of the rock, small fractures occur, generating seismic signals. This process can repeat many times over a short period, producing what is recognized as a swarm. Another contributing factor lies in the extensive glacial cover that blankets Mount Rainier. The volcano supports one of the largest concentrations of glacial ice in the contiguous United States, with ice thickness reaching hundreds of feet in places, roughly 100 to 300 feet or about 30 to 90 meters. This ice exerts a considerable load on the underlying rock, and seasonal changes in snow accumulation and melting can subtly alter the pressure on the volcanic edifice. While these changes are gradual, they can influence stress conditions in shallow zones, potentially interacting with the already sensitive hydrothermal system. The geometry of the volcano also plays a role. Mount Rainier stands at more than 14,000 feet, approximately 14,400 feet or about 4,390 meters above sea level. Its height and steep slopes create gravitational stresses that are constantly acting on its internal structure. Over time, these stresses can lead to deformation, particularly in regions where rock has been weakened by alteration. Small earthquakes can occur as the mountain adjusts to these stresses, especially when combined with internal pressure changes from fluids and gases. Seismic monitoring networks have recorded similar swarms at Mount Rainier in the past. These episodes are not uncommon for this volcano, and most have not been associated with eruptive activity. Instead, they are often interpreted as part of the normal background behavior of an active volcanic system. However, each swarm provides valuable data. By analyzing the timing, location, and characteristics of individual earthquakes, scientists can map the zones where stress is accumulating and being released. The waveforms of these earthquakes also offer insight into their origin. Many events in such swarms are classified as volcano-tectonic earthquakes, which result from brittle fracture of rock. Others may exhibit characteristics of long-period events associated with fluid movement. The distinction between these types is crucial because it helps determine whether the driving mechanism is primarily mechanical stress or the movement of fluids within the system. At Mount Rainier, the current swarm appears to be dominated by small, high-frequency events, suggesting that fracturing of rock is a primary process. This aligns with the idea that pressure changes within the hydrothermal system are causing the surrounding rock to crack. The absence of significant ground deformation, as measured by global positioning systems and satellite-based techniques, further supports the interpretation that no large volume of magma is currently moving toward the surface. The internal structure of the volcano has been studied using a combination of seismic imaging, gravity measurements, and other geophysical techniques. These studies reveal a complex interior with zones of varying density and composition. Regions of lower density may indicate the presence of partially molten material or highly fractured rock saturated with fluids. The distribution of recent earthquakes often correlates with the boundaries between these zones, where stress can be concentrated. Hydrothermal systems within volcanoes like Mount Rainier are particularly important because they can store and transmit heat and fluids over extended periods. Water from precipitation and melting snow infiltrates the ground, percolating downward until it encounters hot rock. There it is heated and can rise again, forming a convective circulation system. This process not only alters the rock chemically, but also creates pathways for gases to escape. Fluctuations in this system can lead to changes in pressure that trigger seismic activity. The presence of acidic fluids in these systems can significantly weaken the rock. Over time, minerals are altered into clays and other soft materials, reducing the strength of the rock. This has implications not only for seismicity, but also for slope stability. Mount Rainier is known for its history of lahars, which are volcanic mud flows that can travel long distances down river valleys. While the current earthquake swarm is not directly connected with such events, the underlying processes that weaken the volcano's structure are part of the same broader system. Temperature gradients within the volcano also influence its behavior. Near the surface, temperatures are relatively low, but they increase rapidly with depth. At a few miles below the surface, temperatures can reach several hundred degrees Fahrenheit, roughly 300 to 600 degrees Fahrenheit, or about 150 to 315 degrees Celsius. These conditions are sufficient to sustain hydrothermal activity and maintain partially molten zones. The interaction between heat, pressure, and rock properties creates a dynamic environment where small changes can have measurable effects. For example, a slight increase in gas pressure within a confined fracture can trigger a series of small earthquakes as the fracture expands and connects with neighboring cracks. This chain reaction can produce the clustered pattern observed in the swarm. Another aspect to consider is the regional stress field imposed by tectonic forces. The Pacific Northwest is subject to compressional stress due to the ongoing subduction of the Juan de Fuca plate. This stress is not uniform and can vary across relatively short distances. Local geological features, such as faults and ancient volcanic structures, can influence how stress is distributed. At Mount Rainier, these factors combine to create conditions where stress can be released in a series of small events, rather than a single larger earthquake. The timing of earthquake swarms can also be influenced by external factors, such as atmospheric pressure changes and seasonal variations. While these effects are generally minor compared to internal volcanic processes, they can influence the sensitive balance of forces within the system. In an environment already close to failure, even small perturbations can trigger seismic activity. Instrumentation around Mount Rainier has improved significantly over the past decades. Modern seismometers are capable of detecting extremely small ground movements, allowing for a more detailed picture of what is happening beneath the surface. Data from these instruments are analyzed in near real time, enabling the identification of patterns that might indicate changes in the volcano's behavior. The current swarm, with nearly 100 recorded events, falls within the range of past activity levels for this volcano. The magnitudes of these earthquakes are generally low, often below magnitude 2, which corresponds to energy releases that are many times smaller than those of damaging earthquakes. Nevertheless, the spatial clustering of these events provides a clear signal that the system is actively adjusting. Understanding the geology of Mount Rainier requires integrating information from multiple disciplines, including volcanology, seismology, geochemistry, and geomorphology. Each earthquake, no matter how small, contributes a piece to this larger picture. By examining the distribution of events over time, it is possible to infer the movement of fluids, the evolution of pressure conditions, and the response of the surrounding rock. As the swarm continues to unfold, attention remains focused on whether the pattern will persist, intensify, or dissipate. The behavior of previous swarms suggests that such activity often diminishes gradually, as the system returns to a state of relative equilibrium. However, the continuation of seismicity over days or weeks can indicate ongoing processes that warrant close observation. The structure of Mount Rainier, shaped by repeated cycles of construction and destruction, ensures that it remains a complex and active geological system. Its current earthquake swarm is a reflection of that complexity, driven by interactions between magma, fluids, rock, and external forces. Each tremor represents a small adjustment within this system, a release of energy that provides insight into the forces at work beneath one of the most prominent volcanoes in North America. Activity beneath Mount Rainier does not occur in isolation, and the continuation of an earthquake swarm often reflects a sequence of adjustments within an already active volcanic system rather than a single triggering event. As the current cluster of nearly 100 tremors unfolds, the spatial distribution of these earthquakes becomes increasingly important. Many of the events are concentrated along specific sections of the volcano's flanks, suggesting that stress is not being released evenly, but instead focused along pre-existing zones of weakness within the edifice. These zones are often aligned with earlier structural boundaries, such as old dike pathways where magma, once forced its way upward, solidified and left behind rigid internal structures that differ from the surrounding material. These internal contrasts in rock strength and composition create natural pathways where pressure can accumulate and be released. When fluids migrate upward through the system, they tend to exploit these pre-existing weaknesses. As pressure builds, the surrounding rock responds through brittle failure, generating seismic signals that are recorded as part of the swarm. The repeated nature of these events suggests a continuous process rather than a single pulse, indicating that the movement of hot fluids is sustained over time rather than momentary. One of the defining characteristics of Mount Rainier is its extensive hydrothermal system, which extends from deeper zones up to near-surface expressions such as fumaroles and hot springs. This system acts as both a reservoir and a transfer network for heat and pressure. Water derived from precipitation infiltrates through fractures, descending until it encounters elevated temperatures. There, it is heated and can become buoyant, rising back toward the surface. This cyclical movement creates convection cells within the volcano, and fluctuations in these cells can produce measurable changes in pressure. During periods of increased hydrothermal activity, the expansion of heated fluids can exert additional force on the surrounding rock. Even a modest increase in pressure, distributed across a wide area, can be sufficient to trigger multiple small earthquakes. The current swarm may therefore reflect a phase in which fluid movement has intensified, possibly due to subtle changes in heat input from deeper levels of the magma system. At greater depths, the connection between the swarm and the deeper magma source becomes a critical consideration. Magma rising from the mantle does not always move directly to the surface. Instead, it can stall at intermediate depths, forming temporary storage regions. These regions can evolve over time, with magma cooling, crystallizing, and releasing dissolved gases. The release of these gases increases internal pressure and can drive fluid movement into the surrounding rock. This process creates a coupling between magmatic and hydrothermal systems, where changes in one can influence the behavior of the other. Seismic data analysis often reveals subtle shifts in earthquake depth over the course of a swarm. In some cases, events may begin at slightly greater depths and gradually migrate upward, a pattern that can indicate the ascent of fluids. In other cases, the depth distribution remains relatively constant, suggesting that the process is confined to a specific level within the crust. For Mount Rainier, the current pattern appears largely confined to shallow levels, reinforcing the interpretation that hydrothermal processes are playing a dominant role. The role of structural stress cannot be overlooked. The volcano exists within a region where tectonic forces are continuously shaping the crust. Compression associated with subduction creates a background stress field that interacts with the internal dynamics of the volcano. When combined with the gravitational load of the mountain itself, these forces produce a state in which the crust is close to mechanical failure in certain zones. Under such conditions, even minor changes, such as a slight increase in pore pressure, can trigger seismic activity. Mount Rainier's historical record provides additional context for interpreting the current swarm. Previous similar episodes have demonstrated that the volcano is capable of producing clusters of earthquakes over periods ranging from a few days to several weeks. These swarms have varied in intensity, but have generally remained within a range of low-magnitude events. The recurrence of such patterns suggests that they are an inherent feature of the volcano's behavior rather than an unusual occurrence. Another dimension of the volcano's geology that influences seismic activity is the presence of extensive glacial systems. The mass of ice covering the mountain is not static, it changes with seasonal cycles of snowfall and melting. During warmer periods, meltwater can infiltrate the volcanic edifice, increasing the availability of water within the hydrothermal system. This influx can enhance fluid circulation, potentially contributing to the generation of earthquake swarms. At the same time, the reduction in ice load during melting seasons can slightly alter the stress distribution within the upper portion of the volcano. The interaction between water and hot rock also has chemical consequences. Hydrothermal alteration transforms original volcanic minerals into softer, clay-rich materials. These altered zones are mechanically weaker and more susceptible to deformation. When subjected to stress, they may fail more easily, producing seismic signals. Over long timescales, this alteration can significantly modify the structural integrity of the volcano, creating regions that behave differently under stress compared to unaltered rock. Geophysical imaging of Mount Rainier has identified several distinct zones within the volcano where such alteration is particularly extensive. These zones often correspond to areas where earthquake swarms are concentrated, suggesting a direct connection between rock properties and seismic behavior. The current swarm's location along the flanks aligns with some of these identified regions, reinforcing the interpretation that pre-existing conditions within the edifice are guiding the pattern of activity. The energy released during each small earthquake is relatively modest, yet the cumulative effect of many such events can provide meaningful insight into the evolution of the system. By calculating the total energy released over the course of the swarm, it is possible to estimate the amount of stress being relieved. Although this energy is small compared to that of a major tectonic earthquake, it represents an ongoing process of adjustment within the volcano. Monitoring efforts extend beyond seismic data. Ground deformation is tracked using global positioning systems and satellite-based interferometry, which can detect very small changes in the position of the Earth's surface. Gas emissions are also measured, as increases in gases such as carbon dioxide or sulfur dioxide can indicate changes in the magma system. Thermal imaging provides additional data on heat flow, revealing areas where subsurface processes may be intensifying. So far, the current swarm has not been accompanied by significant changes in these other parameters. This absence of supporting signals suggests that the activity remains confined to the hydrothermal system rather than indicating a large-scale movement of magma toward the surface. However, continuous monitoring is essential, as volcanic systems can evolve over different timescales. The long-term behavior of Mount Rainier reflects its status as an active stratovolcano with a complex internal structure. Its history includes episodes of lava emplacement, explosive activity, and large flank collapse events. The current seismic swarm fits within this broader context as a manifestation of the ongoing processes that shape the volcano. Each swarm contributes to a deeper understanding of how these processes operate and interact. For those following developments around Mount Rainier, staying informed through reliable updates is essential. If you found this detailed report useful, make sure to like, share, and subscribe, and tap that hype icon to help this video reach a wider audience.